Alright, today we are moving on to Unit 8, and this unit is about exponential functions as well as log functions. And you don't know what a log is yet, but we will get there. But we should know a little bit about exponents. And so this function here's our parent function, and this is the only time in our parent function that we see a number other than, like an invisible 1 maybe. We have a 2 as our parent function. Now this number can be anything, and we'll kind of see what that number does here soon, but this number can be anything. The reason that we don't have our function as this, you don't need to write this down, you can just kind of look. The reason I don't have 1 to the x power is because that 1 to any power is just 1, right? And so if I had 1 squared, 1 cubed, 1 to the 4th power, my answer is just 1. And then that would just be a function that is a straight line, right? Going through 1 at every single x spot. And I don't want that. So as long as our base is not 1, we're fine. So this function here, again, I've got a base 2. The base is the number that is being raised to the power. And if we kind of look at the table that's already filled out for us, don't have to make that this time, we can see that if I am, raising 2 to the 1st power, if I plug that in, 2 to the 1st power is just itself, 2, right? 2 squared, we know, is 4. 2 cubed is 8. 2 to the 4th power is 16, and so on. And so that table would just kind of keep growing. And then we can see here, though, I've got something happening a little bit different. If I'm raising it to the negative 1st power, remember that there's no such thing as multiplying something by itself -1 times, right? That doesn't make sense. So that negative is really saying, how many times am I dividing that? Or moving it to the denominator, really. So here we can say, 2 to the negative 1st power, and you might want to write this down, though. 2 to the negative 1st power, remember that's really the same thing as 1 over 2 to the 1st power. Or really that's just 1/2, right? Same thing here, 2 to the negative 2nd power. We know that's really the same thing as 1 over 2 squared. So that's really 1 over 4, which is 0.25. So when we're raising something to a negative power, we're not going to get a negative answer. I think that's the common misconception. We're going to get a number. It's just going to be a fraction, but it's never negative. It's always a fraction. That fraction is just going to keep getting smaller and smaller and smaller. And so this is where we see this start to appear, right? My line is going to cross through here at 1 because anything to the 0 power is 1. Okay, and I will explain that later. I keep saying that, and I will finally get around to explaining that. But I don't think the video is the time to do that right now. And then my next point here would be move forwards 1 up 2. This point right here, move forwards 2 up 4. And then same thing, I'm just going to slowly decrease. I'm never getting to the negative, never crossing into the negative. That fraction is just going to keep getting smaller and smaller and smaller. And so let's kind of talk about this function a little bit more. But that's what we really want to be paying attention with this function is it's going to get smaller and smaller and smaller moving this direction, but it's never going to be negative, meaning we're never going to cross this dotted green line, which does have a name for it. And then we're going to just increase exponentially. So this line is going to almost become straight up and down. We're just going to start increasing at such high amounts, right? Imagine like 2 to the 100th power. That is a very large number. And so we start to get into really high values for y. So again, my basic function here is just 2 to the x. Or sometimes we just write this as, b to the x power, because that number 2 doesn't really matter very much. We will find out. Okay, so my domain, we are moving from negative infinity, and that looks terrible, negative infinity to positive infinity. Again, that's because my arrow is going forever to the left. We are moving slowly out forever to the right. And so that would be my domain. My range, if I look at, move that back, there we go. My range, I kind of have this cutoff, right? We don't see any value in this negative space, and that's what I said. I'm not going to get a negative number, because anything raised to a power, I'm not ever going to see anything negative, right? We see here that even if x is negative, I'm still always going to get something that's positive. It's just going to be a smaller fraction every single time I move to a negative x value. So my range is going to be from 0 to infinity. And notice how I am going to use a parentheses with that 0 for the range as well, because we're never going to touch 0, okay? So I'm never going to be able to get 0. That's because there's no number that I can plug in for x that gives me 0, okay? Unless if my answer was, unless if I had 0 to the x power, right? That's the only way I can get 0, and 0 cannot be a base for an exponential function. Okay, so remember end behavior. This is saying as I move to the right, what is happening to my arrow? Is it going up or is it going down? Okay, so as x approaches infinity, right, is it going up or is it going down? Well, this arrow is going up. So we can say as x approaches infinity, f of x is also going to approach infinity. And then as x approaches negative infinity, we say, okay, well, what's going on there? So it's very minimal, but we can see that this arrow is very, very slowly approaching 0. Okay, I'm not approaching negative infinity. I know this arrow is kind of slowly going down a little bit, but it's approaching a number. I'm not going down to negative infinity because I can't get to any negative number. So there's no way for me to approach negative infinity if I'm not even in this negative space down here. So we're going to say that f of x is now going to approach 0, and this is the first time we've seen something like this happen. Normally, especially with those polynomial functions, we got a positive infinity and a negative infinity, but now we don't. Now we see a number actually come into play. So let's talk about some other key points. At my x-intercept, I actually don't have one. There is no place where this function crosses the x-axis. And so we will notice that too about this is, again, I'm not crossing the x-axis because I'm not crossing over from positive to negative. I'm sticking to 1. It's either going to be a positive exponential function or, again, we can reflect it and then everything would be negative. But we can't be both. That exponential function is not going to cross 0. My y-intercept is 1. Again, that's because any number raised to the 0 power, and again, that's when x is 0. Okay, my y-intercept exists when x is 0. So any number raised to the 0 power is 1. So my y-intercept is always going to be 1, unless if I see a stretch or compress, and we'll get to that, and my asymptote. So that's how we say that word. That is a line. Okay, that's this green line right here, actually. So that is, we need to write it as a line. You can't just tell me a number. And this is a horizontal line. So remember our phrase HOY. I've got a horizontal line. When I've got no slope, we write that as y equals. So it goes through 0 on the x-axis, so y is equal to 0. Okay, so that's a little bit about my exponential function. Again, even when I am plugging in negative numbers for x, I don't get a negative number for y, I just get a smaller fraction. So we're staying in the positive, we're just going to get really, really small. And then as I move x being larger, as I move x getting more positive, I'm going to really, really jump up. So we're going to be really, really low decreasing here, and then we're going to increase a lot as we move to the positive. So that's our basic function. Now we can talk about standard form. This is also kind of how we can transform it. But as you can see, this way that we transform it is very different than how we transform the rest of them. So this is the only function that we see this year really that looks a lot different. And the letters also mean different things. Okay, so A, this one is still consistent though. A is the vertical dilation, really our stretches or our compressions, right? So that at least is similar. This is also going to represent the y-intercept, and this is very key, okay? This function is, again, very different than the rest of them, so the letters represent different things. So in this case, A is going to represent the y-intercept. So if I were you, I would star that, circle that, highlight that, put it on your flashcard, put it somewhere. That's very important to memorize. That is our y-intercept, okay? So, and that's number in front. And so if we want to even look back at my parent function, there is no A. It's really just an invisible 1, right? 1 times 2 is still just 2. So my base there was 2, meaning the A value was 1, which is why we see 1 as my intercept, okay? B is the base, okay? So this is the number that shows growth or decay, Okay, so that's the number that's being raised to the power. So again, a is the number in front of your base. The base is the number that's being raised to the power. It is also referred to as the common ratio. I don't use that word as much. That might be something more for Texas, because again, this lady is from Texas who makes this. So really, again, just make sure we understand that here a cannot be 0. That's because if it was 0, then this whole thing would be 0, and this would not exist, right? B is also greater than 0. This is also very important. We're not going to be able to take a negative number to the power here, okay? We won't see that, because that leads us into lots of other complications, right? If I'm taking a number that is negative to a power, if I'm squaring it, it becomes positive. If I've got a negative number and I raise it to an odd power, it stays negative. So we see kind of that fluctuation between, oh, now we're positive, now we're negative. So that's not good. So what the rules are on this one, kind of like how in the radical unit, right, we said when I'm square rooting that function, I'm only going to consider the positive. That's the rule. That's the same thing here. My rule is b is greater than 0. So this number is always going to be positive, okay, always. And it also can't be 1. I already talked about that. That 1 to any power is just itself. This number can be negative. A can, but b is always going to be positive, okay? So let's practice identifying some key features and then doing a very, very rough sketch of this graph. So if I had this function right here, again, we want to make sure we understand that this value is the a. Okay, that's kind of its stretch or its compressed. And so that is also my y-intercept now. So I can graph that if I wanted to. We can maybe say that's up high here. That's going to be 40 on the y-axis. And then something that we didn't talk about too much, but we can fill in right here, is if I've got a number that is a whole number larger than 1, we're going to see growth, okay? This is going to mean that my b value is larger than 1. That might also be something that we want to consider, okay? So if I've got a number larger than 1 for my b value, it is growth. And this makes sense, right? If I'm thinking of something like 3, 4, 5, we know that if I square 3 or 4 or 5, that's going to grow rapidly, right? That's going to really build over time. So this is going to be growth. So how we show growth is like this. We're going to start low, and we're going to grow up through that intercept, okay? And then it's just going to get higher and higher. So that would be growth. And that's really it for a very rough sketch of this, okay? And then we can also see decay. And so, again, this number in front, and I like how this is written in 2 different ways. You may see it sometimes as like a 40 and then a multiplication dot. Sometimes you might see it with parentheses. It just depends on, who's writing the problem, the style that they like to use. It doesn't matter. But again, this number in front is my a value. That's also my y-intercept. So this time we are crossing through the y-axis at 6. But now I see a decimal, okay? So now I'm raising a fraction to a power, okay? So this is going to represent decay. So when my b value is between 0 and 1, meaning it's a fraction less than 1, right? Then this is decay. Because not all fractions are less than 1, right? 3 halves would still be growth, because 3 divided by 2 is 1.5. So this would be decay. Again, you don't have to write this, but I'll kind of show us why. Remember, if I'm going to raise 0.25 to a power, 0.25, that's 1/4. So if I square 1/4, that's 1/4 times 1/4, that's 1/8, right? So I'm starting with a number, and I'm getting a number that's smaller than it. Whereas, like, if I took 3 and I squared it, 3 times 3 is 9. That's growth. I'm taking my base, and I'm getting a number that's larger than the base. But in the case of the fractions, if I just multiply more fractions by itself, I'm just going to keep getting a smaller number. 1/4 times 1/4 is 1/8, which is a lot smaller. So this is decay. So that means that we are going to go down. So I'm going to start high this time, and I'm actually going to grow, or I guess decrease, kind of through that y-intercept. So that's what we want to think about there. So we've got 2 different types. We've got growth, where we're starting low, we're growing through that y-intercept, and then we've got decay, where I'm starting high and I'm, going down through that y-intercept. Okay, so then on the next page here, we can use our calculator to complete the table here. And so this is a lot easier than what it looks like, and I've got a lot of words here, but let's fill in the blanks. So this is called the add multiply property of exponential functions. So this is saying if f is an exponential function, if we add a constant to x results in multiplying the corresponding f of x value by a constant. So what this is really saying, I know that was very wordy, but what we're saying is if I am consistently adding something every single time to my x table here, and as we can see, I'm adding 1 every single time. So if I see kind of consistent change in x, I'm adding 1 every single time. So it's not like I'm jumping around and potentially missing a pattern. Everything's increasing by 1 here. What we see is that there's going to be a consistent multiplication with the x or the f of x values, which again, that's just the same thing as y, right? So we should see some multiplication difference, and we can do some of this in our head from the beginning, but we can use our calculator here. So the first one should be pretty easy. If I plug in, to my calculator, 28 times 3 to the 0 power, we know that anything to the 0 power is 1. And again, we follow PEMDAS. So I do exponents before I multiply. So 3 to the 0 power is 1. 28 times 1 is just 28. Again, maybe that's proof to you why that's my y-intercept. Because my y-intercept exists when I plug in 0 for x. Well, by definition of my function, I'm raising it to a power. Anything to the 0 power is 1. Okay, so 1 times 28 just gives me 28. And so then, if I wanted to type in the next one, we have 28 times 3 to the first power. 28 times 3, if we type that into our calculator, just gives us 84. And then I can do that again. 28 times 3 squared, that's really 28 times 9. So in your calculator, you could type in 28 times 9, which gives us 252. And so on. So I am going to give us the rest of the numbers here, so that way we're not just spending a bunch of time typing things in. But our numbers, as you can see, start to get very large, so I'm going to try to quickly write them, and then maybe you can pause and also write them down. But also, this is a good time to ask. I just watched the Super Bowl halftime performance tonight. I really liked it. I do like Kendrick Lamar, though. I think the extra credit question for today is going to be, who has been your favorite Super Bowl performer over the years? Put that in the private comments. Okay, so what we can see here is if we notice our pattern, and this is, again, how we can kind of see, we're asking ourselves, 28 times what gives me 84? And then 84 times what gives me 252? If you don't know the answer to that question, and you're not often going to know the answer to that question, especially because these are large, go in reverse. Divide these two numbers. Take 84, take the second number, and divide it by your first number. You should get 3. So we're multiplying it by 3 each time, okay? So again, you could take 252 divided by 84, you get 3. So I'm multiplying by 3 every single time. So if I can figure out these first couple numbers, all in my calculator I would have to do is do times 3, times 3, times 3, times 3. And that's how I keep filling out this. And hopefully you're noticing that the 3 comes from somewhere in my problem. It's not random. That base is the multiplication factor, which is why we also see, we filled that out, it's also referred to as the common ratio. So whatever my base is, that's what we're multiplying each time by, okay? So the number right here, the a value, that is always going to be this spot in my table. 0, comma, then I fill in the number of my y-intercept, that's my a. Then, whatever my base is, I can take that number and multiply it by 3. And then I keep going, multiply that by 3, multiply that by 3. So that is the add multiply property, okay? So that's how we can easily fill out a table, and we can also go in reverse. I could also write the function if I'm given a table, okay? So for this example, it says f is an exponential function. If f of 0 equals 24, so we can fill that in. F of 1 is 96. we want to find f2, f5, f9, and f of negative 2, okay? But we do have a whole table here if, for us to fill out again as well. So, again, if you are also kind of not remembering this notation, f of x is the original notation. So we say that, f of 0 is where I replace x with 0, right? So we're saying if x is 0, then my answer is 24. So that's that notation. So if I want to know what is the equation for this function, then again, if we can remember that whatever my x-intercept or my y-intercept is, that's when x is 0, that's when we fill that in as my a value. So that's going to be the number that's in front. And feel free to use the dot or use parentheses. I don't really care. But then the base. So that's where I only really need 2 numbers in my table, and I can figure this out. So if I want to know 24 times what gives me 96. If you don't know that off the top of your head, again, you're not expected to, go in reverse. Take this number and divide it by the 24 and figure out what we get. So I get 4 when I type that in, meaning that I'm multiplying 24 by 4 to get 96. So that is my base. And so I can now find f of 2. So I can take 96. Again, I can multiply that by 4 to get that answer. That's 384. So we can fill that out here. If I wanted to find f of 5, then this is also another cool trick. I want to find this number here. So from here to here is what I'm trying to find. So to go here, I'd multiply by 4 once. Then I'd multiply by 4 2 times. Then I'd multiply by 4 3 times. So I can say, I could take that 384 and I can multiply it by 4 cubed, right? Because I'm moving 1, 2, 3 levels down the table. So rather than trying to fill out everything, you can, but that's also another neat little trick. I can also multiply by 4 cubed. So in your calculator, you can type in 384 times 4 to the 3rd power. And we get a very large number here, 24,576. Okay, then if I wanted to find to the 9th power, I would, multiply by 4 once, twice, 3 times, 4 times. So then again, I could multiply by 4 to the 4th power. I get a super, super, super large number. We are in the millions. 6,291,456 would be my answer. And if I wanted to fill in the table as well, because I think the homework does have you kind of filling in the rest of the table too. We don't want to leave them all blank. We can do that as well. An alternative, again, is to type this function into your calculator. Into the y equals spot, type this in. In your calculator, hit the y equals button, type in 24 times 4 to the x power, hit second graph, and then that's a table option. And then now you have your table of values. So that's option number 2. Or again, you could just keep kind of typing in times 4 and get it like that. So either way, however you want to do it is fine, but it all leads us to the same answer in the end. So here's our next set of numbers. Okay, but I really only needed a couple. And then the question is, well, how do I find f of negative 2? That's not on my table. And so, again, if I want to go in reverse, and this is also something that's useful, is maybe I'm not always given, f of 1 or f of 2. Maybe I'm giving something really high and I need to move down the table, right? Let's say I gave you f of 5 and I told you now you need to find f of 1. What would we do? Well, we kind of already talked about it. I can divide, right? If I'm moving down the table or if I'm increasing x's every time, right? Or multiplying, to go in reverse would be to divide by that each time. And so I can divide by 4 to get to the next one, okay? So, and I know we don't need f of negative 1, but I can start there. So I know that f of 0 is 24. So f of negative 1, moving 1 down the table, would be 24 divided by 4, right? So that would give me 6. And then f of negative 2, well, that is 24 divided by, 6 divided by 4, which gives me 1.5. So we can divide down each time. Another way to think about this is, what if I wanted to plug what if that doesn't make sense to you, or you're like, I am going to kind of not remember this. Another option, again, is just to always take that number for x and plug it back into the function. But what's going to happen here? So we can just plug that in, right? So 24 times 4 to the negative second power. Okay, so again, anything to the negative power is writing that as 1 over the function. Okay, so this is really the same thing as 24 over 4 squared, right? Because that 4 is being raised to the negative second power, not the 24, just the 4. So the 24 stays on top. I only need to move what's being raised to a negative power to the bottom. And so this is the same thing as 24 over, and we know 4 times 4 is 16. 24 divided by 16 is 1.5. This is exactly what I did here, right? I took 24, I divided it by 4 once. I took that and I divided by 4 again. Or in other words, I divided by 4 squared. So however you want to think about this problem, we want to remember that when I've got that positive exponent, that's saying how many times am I multiplying that number by itself, right? And if I've got that negative exponent, that's saying how many times am I dividing that number? And so that's going to be very important. So if it got the negative exponent, that's where we see those fractions start to appear. And when we've got that positive exponent, I'm going to get those large numbers to appear, as long as my base is larger than 1. If it is in reverse, if I've got a fraction base, that's where it's opposite, right? Now if I've got a negative x value over here, we've got really high numbers. And if I've got a positive base with that fraction, or a positive x with that fraction base, now I get the low numbers. So we do want to keep those separate. We want to know growth versus decay. But we're used to seeing the growth, right? We're used to seeing my base as a whole number versus a fraction. So the homework for this should be pretty simple. All you're doing is just doing growth, decay, telling me that in words, and then writing the intercept, and then doing a rough sketch. So that's going to look exactly like these two. And then you will then fill out the table, fill out more specifically F3, F6, and F of negative 3. Not all of these are on the table, so if you're wondering, like, why is this separate? Again, some of them will be negative, as well as writing that function. And I do give you a couple of the numbers there. So that's really it. Should be pretty simple on the homework. Number 11 and number 12 is just kind of, making sure you listen to me today, and you can look back at your notes for that. So if you have any questions, feel free to email me.